Okay, I think we can probably go. I'll just put this. So we have another discussion session now. So people have been putting ideas and topics, just like yesterday, of what we can discuss in this class. In this Padlet page. So I think yesterday we actually got through quite a lot of topics and had a really nice discussion. But we have time to continue that if people want to continue it or talk about new things or different things, if people have other ideas of things they would like to discuss. So I guess I'll first open the floor if anyone has anything really burning, and if not, I have a curiosity for myself that I could just go for. But yeah, I'll open the floor. Okay, I will go for it. So I put in a question about whether Lisa will be able to confirm the massive black hole binary candidates that we have. So I think there's quite a number of candidates which are based on periodicity of light curves. And I wondered if anyone knows much about whether these candidates could be confirmed by Lisa. Hands up. I think Maria might have been first.
So I think the candidates we have identified with time domain surveys, it will be very hard for Lisa to say anything because these are quasars that have mass of 10 to the 8 to 10 to the 9, so they're very massive for Lisa. And also we have like 10 to 15 years until Lisa. So if nothing else, we will see if the periodicity persists until then. So if it persists, for most of them, we will have accumulated enough cycles to be confident that they are binaries. I guess the other connection with time domain surveys and Lisa is that we will have LSST, and in that data set, maybe we will find some short period binaries in lower mass AGN, and this will be relevant for Lisa.
Okay. Luke also has some kind of went down. Oh, Marta has a hand up.
Yeah, can I follow up with the question? Probably Maria can address it. So I'm not part of LSST, and so I don't have very good information, partly because I haven't probably read enough material. But is there a task force identified to look for all type of transients that could be also faint AGN? Or are you, because I imagine that people like you are looking into this for at least the bright ones. So are there thresholds in flux? So I'm just asking if for these faint quasars are faint AGN are really part of the analysis pipeline. There are people who are actually going to look for them.
Yeah, so I think LSST has a working group on AGN, and the plan there is to be as comprehensive as possible in the detection of AGN. Now I can talk about magnitudes. So the single exposure magnitude is 24, which is already much better than current time domain surveys. The coadded data that will allow us to find even fainter sources will go to magnitude 26. Mm-hmm. Now, the problem with detecting AGN with the coadded data is that you cannot do the variability studies because they're very faint. Right. That being said, Cheng Xin, who gave a talk yesterday, she has this model that predicts that there should be thousands of short period binaries and even a few of them with 1 to 2 days periods.
I thought that model was very optimistic.
I would agree. It's a little bit on the optimistic side, because they also mentioned that you need to co-add. And I think the way it can work in that case is you have a trigger from LISA, you have a very specific period and very specific part of the sky. And then you know how exactly you can go back to the LSST data and dig from the noise this signal.
And sorry, on this, something that I've been invited to a meeting for Gravity Plus. It was one of those meetings where they invite random people and say, can this instrument do something for you? You are, wow. But one of the science cases, I mean, I think it's so there is a basic science case. So what is Gravity Plus is the empowered version of gravity, so very high astrometric precision and the ability to look for motion in the broadline region of quasars. And so in principle, it should be able to find binary quasars, no, not to find, to study broadline quasars with signatures of duality. I mean, I haven't worked on that, but Tamara and her collaborators have. But on top of it, but it has a field of view is minuscule, so you cannot look for things. But the other thing that I thought was that instead of just looking for binary systems, in principle, sorry, this is not necessarily LISA, it's a bit perhaps PTA, but since you're here, you can ask. But once you have, ideally, if you have from PTA, you have an individual detection. With an instrument like Gravity Plus, you can actually look at the motion of the gas just after the black holes have merged. When you have and that, going back to testing the models, probing the models, and I thought that would be extremely powerful, provided that there is gas, provided that you find the actual host of the PTA emitter. Is there, I don't know if this has been publicized much besides the Gravity Plus community. In general, I mean, the instrument and its capabilities.
So I think when it comes to the method of broadline shifts to detect binaries, they cannot detect the very compact binaries. When they get to very small separations, they cannot support broadline regions. And Luke Kelly has a recent paper on that. So they can probably give us the population that are at 0.1 parsec.
No, exactly. So that's why their science case is to find, is to look for binaries. Mm-hmm. My science case is instead to look, once you have a binary, you can actually look at how the gas in the circumbinary disk is behaving. Mm-hmm. Because I think that I can mention that Julian Kralik is very skeptical about anything that has to do with models of classic broadline regions. And in general, all our models of circumbinary disks, and mini disks are very idealized. So we don't actually have anything that probes the gas at that depth.
Yeah, so we need to have a candidate that is relatively nearby, because if you look, for example, at the sample of periodic quasars, the resolution you have for even resolving the binary, it's micro arc seconds, which is at the level of the Event Horizon Telescope and below. So you need to be lucky to have one that is relatively nearby to be able to do this detailed analysis of the gas.
Yeah, I think that this is the type of resolution, angular resolution that they're talking about. So I think that, I mean, if there is one in the sufficiently close universe. Thank you.
Marta, do you know what type of information they get about the gas? Like, is it the density or what they're hoping to get?
No, it's in, sorry. No, actually, since it's astrometry, you don't, well, you can recover the density with some models, but what we actually see is the motion of the gas. So you can track how the gas moves. You know, they've done it for, so the most famous case is for a Sagittarius A star, where they track the hotspot. But then for a few quasars, whose names right now I don't remember, but I think one of them is also 3C273, the first quasar ever discovered. They have actually been able to resolve the broadline region and have, for instance, inclination, size, and you know, things like inclination, size, and really the motion of the gas near the binary, if there is a binary. I think it's something that would be helpful to constrain models of circumbinary disks.
Yeah, nice. Thank you. Does anyone have anything they want to from the room, from Zoom, want to add? Yeah, Luke, did you want to say something?
Sorry, I couldn't really hear the question there.
Oh, sorry, I was just saying, did people want to add anything? And we noticed your hand went up and down, so we wondered if you wanted to say something in.
Yeah, I think that was just before Maria answered the periodic variables question. I thought she answered it excellently. My only additional point was that, and I think this might have been said, it was just that the periods there are years, right? So they're well outside of the LISA band, and just the like kind of prior probability of seeing a periodic variable binary AGN source in the actual LISA band is very low. Yeah, and I also agree with Maria's comments about the broadline regions just not necessarily being the best probe for the binary separations that we're interested in. But yeah, I really appreciate Marta's point about just being a general constraint on the gas dynamics in the circumbinary disk portion of the regime. So that's definitely exciting. Something else that could be better for this regime is the iron K alpha line, because that's produced much closer into the central black hole, so it's able to probe smaller separations. So if there are, good X-ray surveys with very high spectral resolution, that could be another tool for LISA sources specifically.
So question, is there any X-ray instrument that could do this? I mean, considering that Athena now is going to have some issues, I mean, I haven't followed the landscape of X-ray satellites. So among the small missions, is there anything that does X-ray spectroscopy? I don't know if anyone is.
Yeah, I don't know, but hopefully somebody else here does.
I'm not an expert on this, but I think the trick there is you need very high resolution spectroscopy. And I thought something like Hitomi would have this capability. So maybe what is Hitomi to GRISM, how they call it. So maybe that's the solution.
Yeah, because with Athena, I think that the situation is not as bright as we thought it was 2 weeks ago.
Oh, sorry, Lisa.
Since we are talking about binarity signatures, I actually, when I was doing the summary of the chapter 2 of white paper, I learned a lot about electromagnetic signatures, and I learned actually that even the panchromatic emission of the AGN disk in principle could lose some, some regions if there is a cavity. that is excavated by the binary, like the mass ratio is close enough. So I was wondering if there is any candidate that has been already found with this technique, and if not, if there is any perspective to actually use this technique for finding binaries. I was just curious.
So I can give you a very short answer. There was a candidate that came out around 2015, and then people have claimed that the claim there was that they see the dip in the spectrum from the cavity. And I think what a rebuttal paper claimed was that they see an effect of the dust. And my understanding is that the models are not that clear, because some models predict a deficit of radiation and some models predict an excess of radiation from the shocks from the streams that come into the cavity. So I think even from the theory side, the signatures are not very clear.
Thank you.
Okay, since we're talking about controversial results, how about TikTok? Do you know what I'm talking about?
The group from Milan may have more to say about that,
No,
because I saw
exactly.
a recent paper.
So do we have anyone who was on either paper and can give us a...
Well, yeah, Elisa, if you go ahead, you can. Otherwise, I can say something.
Oh, but Matteo, I spoke too much in those days.
Oh, yeah. So we were very excited about the paper because, yeah, you know, maybe if there is a candidate, it's always a good news. And then with Massimo as main leading author of the task, we managed to get some additional observations of this candidate with a telescope that is called REM. And essentially what we have found is that there is essentially no signal of periodicity. So probably our opinion is that this is not a binary black hole candidate, yeah, anymore. But yeah, it was an interesting guess.
I will double this. How about OJ27? And perhaps, before before spitting names, we should give a couple of words about the sources, because not everyone perhaps has read all the literature. But so OJ27 is a quasar that for a very long time now has been proposed as hosting a binary because of a of periodicities in the light curve that could be explained by a binary. No, although and interestingly, the TikTok paper, which completely recycled their model to explain their source without. So does anyone have a particular feeling about that source? I mean, the group that has been studying it now for, I don't know, 20, 30 years. They have very detailed models of the binary. I don't have the expertise to judge it, so I don't know if someone can say something about this famous object.
Lots of shaking heads.
I would say something quick. So this is a bright blazar, and it has a light curve that has covered 100 years. And we see these repeated flares every 12 years. If you look at the data, the first, 50 or 60 years of data, they're very sparse, but you can sort of tell where the flares are. So I think there's a lot of confidence in the community that the flares have repeated enough, and at the times we expected them to believe that this is a binary. I think the exciting thing would be to resolve this binary if it's possible. And I think maybe the Event Horizon Telescope collaboration is working on that. I'm not a member, but that's what they say.
I would say that personally, I'm much more skeptical about OJ287. I mean, I think it's fairly convincing, but still not 100% that there is a periodicity there. But that there's good reason to think that it's a binary, I find much less convincing. So I mean, the models are like pretty specific. So like there's a very large parameter space and there's a fairly narrow part of it that seems to match the observations. Blazars are extremely messy and weird and flaring all the time. Yeah, so I'm still skeptical. From a priors perspective, if you look at the actual parameters inferred for the system, it's also just kind of unlikely that this would be a system that we saw. But that's of course not a great reason to say that it's not a real source.
So, Luke, are you skeptical about it being periodic or about the model that describes it?
A little bit of both, but mostly the latter, mostly that it's a binary producing this. I mean, there's, yeah, especially with systems that have jets, there's all sorts of different characteristic periodicities that you could see from warps, from precession, from, you know, lumps in the disk, like all sorts of different reasons that you could get periodicity.
I think I remember reading in the last couple of years it was expected to flare again, but I don't remember seeing whether or not it did. Does anyone know?
I think the flare happened when exactly they expected it, and there's probably another one that is coming up. I'm not entirely sure. I think the thing with the previous flare, it was the source was very close to the sun to be observed with optical telescopes, but they had infrared data and they managed to see the flare. So there's also this part, like you have one flare every 12 years and you may miss it because it's an unfortunate timing.
I mean, ultimately, I think part of what we're learning from the periodically variable AGN candidates, like the ones from Maria or from Matthew Graham, is just that you not only do you need to be comparing to specific noise models, like damped random walk noise models, but you also need just extremely good noise models if you're looking for a 1 in 1,000 type outliers or 1 in 10,000 type outliers. So in the case of OJ287, there is no good noise model that you're comparing to. I mean, people haven't really done good studies of, what types of intrinsic variability you could have in these blazar systems. So without some sort of like careful model comparison like that, I think that's what's really missing for me. Yeah, like looking more carefully at the overall population of all blazars, looking at their kind of variability patterns, their power spectra, and really comparing those. I think that's kind of what's missing to me.
I don't know if people know about this, but there's also another candidate that came out the last year. It's also another blazar. And this is from, I think, 40 years of data. It has a periodicity of something like 5 years. And it has a first part that it seems like a sinusoidal periodicity, then a second state that nothing happens, and then another 3 or 4 cycles in the end that the periodicity appears again. I think the interesting part with that source is that the periodicity appears exactly in phase with the old sinusoidal model. And that has also been claimed to be a binary, although it's hard to exactly explain the intermediate time that it doesn't do the periodicity. Does anyone have ideas on this candidate?
Thumbs down.
So I think Luke has the bar very high. That's why we call them candidates, because we cannot be sure. So since we are at the point that we don't have any confirmed, I think we can be excited about the sub-threshold and sub-exciting ones.
I 100% agree that it is a candidate. I mean, we always talk about how the best way to test these periodic sources is to wait and see if the periodicity goes away. And that's exactly what we see in this source. So.
My problem with this source is that it's hard to either confirm or disprove, because if it goes into the other state, you can say, oh, it's at the state that it's not periodic anymore. And maybe at some other, I don't know, 10 or 15 years, it will start being periodic again. So I think this is a problem with this source.
Yeah, I guess one comment to be like a little bit pessimistic about my pessimism is that in many of the kind of detailed circumbinary accretion disk simulations, you can see these kind of secular state changes between when accretion is favoring one source and then favoring the other source. And I think in those transitions, then you do actually lose the periodicity, but you can also lose the phase lock. So you wouldn't expect it to come back in phase also. But that's also always something that's really worried me, is that, you know, maybe in the most ideal situations, you do actually lose your periodicity. Maybe it comes back in some other weird way. Yeah, it's just such a messy problem. I mean, I think to confirm or to develop confidence in an electromagnetic counterpart or in an electromagnetic binary candidate without a gravitational wave counterparts, we need multiple different methods of indicating binary motion. And yeah, that was kind of my goal in doing this spectroscopic or kinematic offset analysis. But unfortunately, I found that the parameter spaces just don't overlap almost at all. So the situations where you get the spectroscopic signatures, there's no hope of seeing the periodicity and vice versa. So that made me very sad. But yeah, I mean, maybe some of these like spectroscopic disk features, like I think it was Eliza mentioned, like maybe that's another good way to go.
Yeah, except that also those are extremely hard to actually prove. I mean, a dip in a quasar spectrum, I mean, you can get it in 100,000 ways. And also, yeah, I think that finding an excess is easier than finding a dip in many ways. I mean, it's something that is more, and dust, I mean, as I think Maria just explained, yeah, dust does the job very happily and without problems. So, oh.
And I think something missing from the kind of circumbinary accretion models is like good radiative transfer. I don't think anything has been done there, at least not where you have like enough time to really get a secular steady state.
Yeah. Well, Davilar this morning said they're starting it. So I'm actually looking forward to see the results. I'm very curious.
Yeah, that would be excellent.
Yeah, I suppose if people have other questions and topics they want to bring up, or something that I guess if you wanted to talk about something all week and haven't had an opportunity, now's your moment. Oh, Maria.
So I had an idea following up the discussion we had yesterday, because we sort of discussed how it is very hard to bridge the gap between pulsar timing arrays and LISA. But there are these ideas that maybe Gaia can bridge the gap in between, or even astrometric observations with the Roman telescope. So I was wondering if anyone has more expertise or ideas on that.
I did a little bit of work on this with Jonathan Gare, simulating how well you can measure gravitational waves using the astrometric method. So if people aren't familiar, the idea is that the actual positions of background stars will also be systematically deflected as gravitational waves pass by. So I think the issue with Roman is that the field of view is way too small. You need a really large fraction of the sky to be able to kind of beat down the noise on these detections. So I mean, ironically, the actual like angular precision would be good enough, I think, but you need a huge fraction of the sky. And then with Gaia, it's the opposite issue. You just don't quite have the precision, but you do have the fraction of the sky. That being said, I think Gaia actually comes oddly close to being able to do it. So if you imagine whatever the follow-up to Gaia is, the next all-sky astrometric mission, I think even if you improve your angular resolution by a factor of a few, like 3 to 5 or something, I think then you actually have a oddly good chance of being able to observe this, which I was kind of surprised to see.
And which frequencies would that, so what type of sources would that detect? So Maria mentioned in between LISA and PTA.
Yeah, so it's just determined by the kind of Nyquist sampling. So your lowest frequency is just the overall baseline of the survey. So 5 years for a 5-year mission or something like that. And then the high frequency is mostly just from the kind of the cadence of sky coverage. And then that can be like actually quite high, which is why you get up near the LISA band.
Okay.
Can I ask a question?
Yeah, please.
Can you detect a stochastic background or single source? I mean, I'm not familiar with this. I'm just asking. I mean, I don't know.
Yeah, I think you can do both. The modeling I did was for individual like continuous wave sources. In that case, it's much easier to beat down the noise. So I think for a stochastic background, you would have kind of a much higher noise level, but it's not something that I've modeled personally.
So look, for the case of individual sources, I guess the signature you see is more localized to a part of the sky, whereas the background is the entire sky. So maybe you can be lucky with the Roman and you have a binary in that part of the sky.
No, it's actually still all sky. So you'll see this still like quadrupolar type distortion. So yeah, it's hard to kind of describe it visually, but yeah, it is kind of an all sky signal, and you do still kind of require that full sky aspect to be able to beat down the noise. So one good example is with Gaia, it has these two different cameras, and they're offset by like 104 or 107 degrees, and there's a very small oscillation between the two. Just there's some mode of the physical instrument that oscillates a little bit, and that imprints this variation on the sky. That's a huge noise source. So you need to be looking at the entire sky to be able to beat that down, essentially, to constrain that.
And maybe related, can you constrain also on the mass of the eventual single sources or the redshift? No, I guess. Oh, yes.
So you can definitely, you get some measurement of the sky location. I think that's actually quite good. Intrinsically, you get an amplitude, but nothing about either the masses or the distance. So you would have to get that from a counterpart, I think. I think that's the case, but I would have to double check to be sure.
Is there like a Gaia follow-up on the horizon with resolution? Or not trying to do it? Okay.
I just put in the chat the paper by Christopher Moore that does kind of a analysis of the astrometric surge from a few years ago, if anybody's interested in it.
Nice. And Chris is probably in the corridor, in fact. I'm cornering.
Well, I'm grateful because now I finally understood the section that we had in the white paper about this. I was editing it and I had no idea what it was about. So in retrospect, I will go back to what I did. I can bring up another controversial topic for which we have candidates and only candidates, intermediate mass black holes. So when do we think that the candidates will actually be intermediate mass black holes for real? I mean, apart from the low mass ones that LIGO and Virgo and Carter can see.
I guess the question is, what would it take to convince you? And I'm not very familiar with what candidates we have and what is the signatures that we're looking at.
Yeah, we have candidates of a variety of types. So some of them are, either high luminosity X-ray sources. Most of them are not in galaxy centers. They're typically somewhere in a galaxy. And in those cases, so they have been either selected as high X-ray luminosity sources, so more luminous than the ULXs, which are ultra-luminous X-ray sources, which are too luminous to be a neutron star, or now they're mostly considered to be super-neutron black holes. Very often you see a radio jet. What you don't have, so basically you can estimate the mass from the SCD or from the fundamental plane, so always scaling relationships, but there is no mass measurement. So when will we be happy of something that is a candidate without actually measuring the mass? It's the same thing that as we have for binaries. Will we ever be accepting something without an actual measurement of the mass to be an intermediate mass black hole?
I think there is an argument with the minimum variability you should expect that is determined by the size of the source, like the light crossing time or something like that. So I don't know if we have this type of measurements for these sources and what sizes they suggest.
Yeah, I think that the only one that has been monitored for a very, very long time is HLX1. So this is the only source for which there's been work done for a very long time. So it meets all the criteria, except that the mass is inferred and not measured. So, do we have any smart way to measure masses that, that we haven't thought of yet? I mean, the usual point is LISA is sensitive down to mass about 10 to the 4-ish, 10 to the 5. So at the moment, if we look at the number of black holes that we have with measured mass in that range, I think it's less than 5. So we're extrapolating to the whole universe based on 5 sources. Sometimes makes me feel a bit uncomfortable.
So I have a very naive question concerning this. So is there any chance, probably not, but is there any chance to have like a maser emission from the accretion disk of those objects? Because,
You can have an estimate.
those are proven to be very good ways of measuring mass. Of course, you have to find them.
No, but you can always estimate the mass. You cannot measure it. That's the point. I mean, to measure mass, you need a dynamical way of measuring. So you can use the accretion disk. Basically, it allows you to measure the ISCO, and so you get the mass with some assumption on the spin. But it's not a dynamical measurement.
Maser would be, no? Because you,
Sorry?
if you have maser emission, would be.
A maser, yeah, oh yeah, that's a Keplerian disk, but you get at the moment it's only 10 to, the lowest mass masers that have been found for the moment is about 10 to the 6 solar masses, but that's a dynamical measure, so it's not from the luminosity of the accretion disk, it's really from the velocity that you measure.
Sure.
So my guess with that would be, if we have a large enough sample, we will start building our confidence in the same sense, like short gamma ray bursts. We hadn't seen that they are from a neutron star merger, but I think we started, the more instances of the phenomenon we had, the more we built our confidence that this is the source. And I think that happens quite often with astrophysical sources.
And perhaps, I don't know if Martin is in the audience, with TDEs, is that something that, besides an estimate of the mass, can you actually have a measurement of the mass in some way, perhaps, even using gravitational waves as you are?
I wanted to comment on this. Yes, we can, but I was thinking that maybe I'm not sure, but because it was in my mind a work that I did with some researchers from Pavia, where we were studying a partial tidal disruption event. Well, we were studying an event we were like a quasi-periodic eruption, and that they observed with XMM Newton, and we tried to interpret this event like a partial TDE, which seems the most reasonable way to explain from a physical point of view this source that you observe. And it is interesting because in this source, if our interpretation is correct, actually the black hole mass that we infer is 700 solar masses. So it's an intermediate mass black hole that is in a range so far we don't know from observation. But I mean, yeah, I agree with you, because with only electromagnetic radiation, you can just infer. We need the combination of gravitational waves and electromagnetic radiation, but so it's something that we need to wait years. Because all the papers that I have in my mind that aim to have observed an intermediate mass black hole, and because there has been something like a tidal disruption events on this black hole, they just suggest some ranges of masses. I mean, because I have in my mind two tidal disruption event candidates. One where the mass suggested was in between 10 to 5 and 10 to 6 solar masses, so it can be actually it's quite massive, not really intermediate mass. But another one was between 10 to 4, 10 to 5. So the range that was actually pointed out seems to be in the proper interval to say, okay, this is intermediate mass black hole. But yeah, I think the best way is to wait for gravitational waves or some kind of I'm not sure it's really useful, but maybe some because in principle we can have also some electromagnetic radiation during the disruption phase. So if we could combine both the electromagnetic radiation from the disruption phase and the one from later stages, with more information, it could be more precise, the estimate of the mass. But these are the main ideas I have in my mind. So yeah, right now it's quite difficult to measure it in a clever way. I agree.
How long, I don't know much about this topic, but how long are these candidates? Is it like happens over observations over a few months or days or?
You mean a full disruption or a partial one? Because a partial one can actually continues also for many, many years. I mean, in this case, one thing, okay, for instance, in these sources we were studying that we think is a partial TDE, we asked for some more time of observation because we could estimate the time we think the star will be completely disrupted. So, of course, if you have something to think is a partial TDE with an intermediate mass black hole, and you can have like all the time you want with the telescope to observe the electromagnetic radiation produced, and then you see also the flare of disruption, you have a lot of data, you can build a very precise model, and you can estimate in a precise way the mass of the compact object involved in this event. But I mean, you need the time of the telescope. For instance, we didn't manage to get it, so the source is there, and we cannot do any other prediction. So,
is it like X-ray or something else?
this was in X-ray, but yeah, TDEs emit over X-rays, optical, also infrared. So it really depends on the specific event.
To go to? Oh yeah.
To look for them, and then we have Anna who was looking, or she was an honor student who was looking for the triangle. Oh, but I think we stayed just looking for them. But it's possible.
Any other?
I mean, sorry, just
Yeah,
since there are no other points for the moment, because there is also another way I was thinking that, but not necessarily the disruption events in general, but this is, I think, very unlikely to measure. But if an intermediate mass black hole is a lens for some events, in this case, I mean, this can be a way to estimate the mass of this object. But it's like, I mean, it's very difficult to make a prediction because we have no idea. First of all, if these objects really exist and how they're distributed in the universe. So we cannot do actually distribution of lenses, which is very reasonable. So, I mean, it's very difficult to make prediction. And but this could be another.
Actually, there are some observations of lens gamma ray bursts. And they say, I mean, I don't understand anything about lensing, zero, okay? So they claim in the paper that the only type of lens that can be explaining what they see is an intermediate mass black hole of mass 10^4 and 10^5. But then they go on, and so there are two papers, or perhaps 3 now. And then, you know, they from just the chance of observing one, they calculate the number density of these intermediate mass black holes, and it's enormous. It's like 3 orders of magnitude higher than any theoretical prediction that we have.
Okay. Okay.
So I mean, I'm actually, I didn't hear about this. It was a journalist who asked me to comment on this paper. That was, wow. And so I've been asking to people doing substructure and lensing to tell me something about what they think of this paper. And they're all too busy to answer because obviously, I mean, they don't care about intermediate mass black holes, people working on lens. And so I still have this enormous curiosity. And so if anyone knows anything about this area, I'm more than happy to share the papers and hear what you think about it.
If you want, I will be happy to read the papers. So yeah,
Awesome.
sorry, I don't.
Yeah, no, again, I will send you my, the links, and also why I'm so shocked by these numbers. I mean, of course, we can be totally wrong in the theoretical models and have thousands of intermediate mass black holes around us.
But The problem is that if the number is so high at some point also, I mean, I will be very happy actually because it's something I study, so I will be very happy, but it's also like at this point quite normal to ask if the number is so high, why so far we just have candidates. It's a bit,
It's very easy, yeah, it's very easy to hide them in the sense that, you know, capturing gas or a star is very unlikely. But I mean, I've honestly, I've never run models with such high number densities simply because I always thought that they were unreasonable. So Martina, I'm more than happy to discuss more because this has been bugging me for now several months. Thank you.
thanks to you.
So out of curiosity, since I didn't know about this, are they even claiming this could be part of the, you know, the dark matter?
Sorry?
Those objects are so many. Could they be like a non-negligible part of the dark matter?
No, not enough.
Too low.
Because I mean, so the number density, so I have to check the calculation that I did, it was a few months ago. So I think it's 1,000 times higher than what we predict normally, 1,000 times or something like that. But since the mass density in black holes that we predict is tiny, it would not compensate, it would represent still a very small fraction of the total, you know, omega in the universe. So, but yeah, I mean,
Or, I mean, they're assuming this intermediate mass black hole distributed randomly in the galaxy, in globular clusters, in the center of the galaxy.
They're not assuming any, so they're finding a lensed gamma ray burst. And they say that they can rule out, but in one line, that they can rule out a dark matter substructure because it's too shallow and they really need a point source. And then to estimate the number density, they just assume a homogeneous, I would say, distribution, so uniform. You know, you just extrapolate from 1 to how many you would need to make this detection based on one point.
It's a bit dangerous, I think, to do this kind of extrapolation, but I think they also say something like, so far, it's the first event of this type that we managed to see lensed, so this means that the number, okay, but still, if there are so many intermediate mass black holes, we also should observe a more lensing effect related to them.
Well, they already found 2 or 3 of these objects. So as I said, this is something that's been, for me, inexplicable. So anyway, I will email you separately, Martina, so perhaps you can explain me something because I'm still very, very surprised.
Okay. Does anyone have a comment back or another topic they want to talk about? I guess it's getting late in the meeting. People are getting tired. There's nothing from the room. Is there anything from Zoom land? But if not, I think you know, we could call it.
Are we still meeting at 7 p.m.? I mean 6 p.m.?
It's a good question, right? On the schedule, there's a wrap-up session. I think it may depend on what happens with the other groups, in fact. But yeah, maybe I'll go and check what's happening. And but if people need to go, obviously Hi everyone. So the session in the other room is still going. So I think I know I spoke to Valeria and she said that Shane and Luca are quite keen to do the wrap up so that we can like swap goals with each other. And I think Marta, would you also be keen to do that? Excellent. So my suggestion is that we have a break now, and then we'll come back as scheduled on the agenda. But of course, if you need to go, that's totally understandable for people on Zoom and in the room. So if you do need to go, thank you. It's been a lovely discussion, really nice few days together, and thank you everyone.
Thank you, Hannah. See you later.
Thank you.
Yeah, thanks so much, Anna, for doing all of the management and logistics over there.
It's a team effort, so thank you. Yeah.
So we wanted to take like some time just to conclude and recap. And I guess I'll call to more senior chairs to take the lead here for now. And we will try to complement you guys.
I don't know how we got roped into that.
Yeah, I was not told about this.
Oh, good. You can go first then, Marta.
Awesome. Okay, so I also had volunteers to take minutes of this session and circulate a summary afterwards. So forgive me if I am not always on top of things. So I can start by giving a short recap of what happened in the Massively Called Catalog project room. So if Valeria yesterday was a success to find one coordinator, we found 5 + 1. So it was very successful. I think it was a good interaction. So there is a good diversity of expertise, career level, and gender and geographical distribution. So this was, it all happened naturally, just people volunteering. So it worked very well. So there are more thoughts on the Google Doc, and the plan is to start with meetings with the group in September.
Okay. So we don't have Lucio, but maybe somebody from the binary disk project, like 2 words, what maybe your next steps and things like that. Things that was said.
I'm really not, I mean, I was listening into the discussion, but I really wasn't involved enough to comment. I don't think I mean, lots of discussions were made on code comparisons, and a lot of progress was made towards setting up sort of a unified framework to allow this to start happening. Same thing.
Is there any
and it's something basically Lucia and Andrea prepared a list of things to do, and they also
I'm sorry, I cannot hear.
Yeah, that's.
I can come closer. Okay, I don't. Okay, so Lucio and Andrea selected a list of codes for the comparison, some with codes, some SPH codes, or other codes. I mean, I think so far they selected around 7 codes, and also a few people to run simulation on this code. And then they also have this idea that they want to divide the project between people that do the simulation and the people that take the data and analyze everything in such a way that also people with less expertise on the topic can be involved. I mean, you can teach them which kind of analysis you want on the data, and so they can learn step by step. And his idea, Lucio's idea, was to circulate an email, if I understood correctly, to all the astrophysics working groups, so that still people can read the document with all the notes and think if they want to join the project or not. And maybe also do a call with the people interested by the end of the summer to start understanding better which are the various leaders for the different codes and how to organize better the whole project. So this was were the main topics discussed.
Okay, thanks both. And I don't see Alexei here, so maybe Shane, we were sharing today. You can say a bit more what we have decided. The multiple for comparison
Yeah, so the ultra compact binary code project, we largely continued our discussion from yesterday. We have not recruited a coordinator yet. So Valeria and I will kind of keep things moving along. We did identify codes, much as the Black Hole folks have. There's a long list of them, but we've narrowed it down to 3 or 4, which are kind of commonly used, currently used, have been used to produce LISA results. And we have coordinators for a few of those. So Alexi and Katie Brevik, and we will slowly pursue the others. Like the Black Hole Project, Valeria went and spied on them and figured out what their schedule was going to be. So we're following suit, and we will kind of really ramp up when fall gets here. But in the meantime, we had yesterday, Heiss had suggested we start a literature survey about the ultra compact binary results for LISA that have been put in the literature already. And so over the summer, for those who are able and interested, we will have a little summer reading club and some discussions to kind of dissect those and understand what the landscape is before we dive into an actual code comparison. So I think that's where we're at. We have a really nice cross-section of folks who participated, which involve both the folks who do modeling, our observer colleagues, as well as our data analysis colleagues. So I think we have a good framework of people to really not just address the problems we set out to in the project, but to really start talking about some of the interfaces between those 3 communities, which we often struggle with, and it'll be good to start working on. So so I think that's where we are in that project.
Sorry, just one question. When you say summer reading club, you will actually organize meetings, or is it organized, self-reading?
Well, yeah, I think, at 0th order, we'll say, this is what we're going to read and discuss. And then Valeria and I hadn't really sat down and talked about whether or not we should or how often we might get together. But in my head, I was imagining we would get together, kind of like Journal Club, for an hour every couple of weeks if we could. So summer holidays obviously will interfere with that. But yeah.
I was expecting maybe a few telecons per summer, and we can go through some of the papers and
yeah,
together for comparison.
Okay.
Is it all on the project?
Sorry, I missed that, Valeria.
Is it all on the project?
I think so.
I think so, yeah.
Okay, then I guess I can move and start thanking our local organizing committee. So Elliot, Andres, Hannah, and Nate, who was very strong, and even despite the illness, chaired and contributed and have been with us during these 3 days. It was our pleasure so I guess on behalf of all of us, it was and the Institute, it was our pleasure to host you guys both in person and online. It was very fun to have so many young people here, and we get to know each other a little bit more. And I guess it's a good start to, to have some collaborations in the future.
And a big thank you also to Valeria. I
wasn't including myself here, but since I'm speaking.
Yeah. So, yeah, let me just also, as your co-chair, Valeria, let me just say thank you so much for hosting. Marta and I have been participating virtually, and it's certainly been a really great meeting, even though we've been far away, and you all have done a spectacular job of organizing it, making it easy, keeping records and everything that will be valuable as we go on. So I think all of you really deserve a real tremendous thank you for a tremendously well done job. So
thanks. And I guess if we're thanking each other, we can say equally thanks to you for putting the science background of this meeting and for chairing and supervising everything that needed to be supervised and chaired. So thank you. And I'll conclude with our attempt to take the group picture this afternoon. So of course doesn't include everybody, but at least part of the group. We will get in touch with the LISA social media team to propagate this through the social media.
That's great, but next time we should have the short people on Zoom be in the front. Lucio's hiding back there too, isn't he? Yeah.
Okay.
Yeah, true.
Is there anything else we should mention?
I think we're good.
Yeah, and you all, all the log definitely serves a very, very long, awesome weekend. I can imagine how tired you are. So enjoy this weekend.
We will try to collect all the links that were flying around and put also the presentations, and we will try to keep it all on the meeting schedule or somewhere in the Astro working group repositories as well.
Yeah, we should move it to the wiki or somewhere where they'll live indefinitely, I think. Yeah.
But that's after the weekend break. So
Yeah, that's right.
Okay, then have a nice day, afternoon, morning, and see you next time. Even the owls now, our cameras are tired, so they don't want to. So have a nice day, and see you next year, and we will keep in touch via Astro Working Group email, please.
Okay. Bye. Bye, everyone.
Bye.
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 Thank you, Valeria. Thank you, team.
Thanks.